Hello and welcome to this online lecture. My name is Patty Kokish and today we're going to be covering material from your online Math 136 class at Ivy Tech for week 14. You may want to go ahead and grab a pencil, calculator, and a piece of paper because we're going to be solving equations today that can get fairly complicated. So you might want to write some of them down so that you're able to do a little bit of work. So we're going to start. We're just doing one section today, section 12.1. This is the last new material for your online Math 136 class. So it's going to be kind of a shorter presentation today since it's just one section. But what we're going to do is we're going to solve systems of linear equations using substitutions and elimination. So we're going to start with kind of simple representations of two equations with two variables, and then we're going to move on to three equations with three variables, which is kind of the important new thing that you're learning in this section. So if you have two lines that intersect, then the system of equations has one solution given by the point of intersection. So if you look at this pink and blue line here, your solution would be the point at which they intersect. This system is considered consistent, and then the equations are called independent. So intersecting lines, system has one solution, it's consistent, and it's independent. Now we can also have the situation where we have two lines that are parallel. In that case, the system of equations has no solution because the lines never actually cross or never actually intersect. So the system is inconsistent. And then we could have two lines that are called coincident, meaning that the system of equations has infinitely many solutions. So if you look, this is a purple line. This is actually a blend of our pink and our blue line. They are right on top of each other, so they're actually the exact same line. So this system is called consistent, but the equations are considered dependent instead of independent. So the system has infinitely many different solutions. So let's look at an example here. Let's say we want to graph the system. We have 2x plus 3y equals -3, and we have 4x minus y equals 3. So what we probably want to do is go ahead and get this in slope intercept form, where we have y equals mx plus b. So what we're doing for this first equation is we're getting y all by itself. So if you look at this first equation, if we subtract 2x from both sides and then divide everything by 3, we'll be left with this right here in this blue box, y equals -2/3 x minus 1. And then down here, if we get y by itself, we would subtract 4x from both sides and then divide everything or multiply everything by a -1. So we'd get y equals 4x, which is going to be positive, minus 3. So these are our two equations. And now it shouldn't be too difficult to graph these. If you take a look, let's look at the red line first. The y-intercept is this -3 right here because it's always y equals mx plus b, where b is your y-intercept. So we go down to -3, and then the slope is 4, meaning that we should go up 4, so 1, 2, 3, 4, and then over 1 to get a new point. So this is our red line right here. And then if you take a look at the blue line, it has a y-intercept of -1, and then the slope is -2/3, meaning that we can go down 2 and to the right 3, or I could go up 2 and then to the left 3. So the two lines intersect at the points 3/7, -9/7, and that is the solution of the system of equations. Now this is kind of difficult to tell what the exact point is just based on the picture because we can't really tell if this is 3/7 or 4/7. It would be too difficult to guess. We don't really have any idea. So what we're going to be doing next is actually solving this algebraically. So from the picture we can tell that we have exactly one solution because our lines intersect in one point. But from actually doing it algebraically, we can get what the exact point actually is. So let's take a look at this example here. Let's say we have 2x plus y equals 5, and we have -4x plus 6y equals 12. So we're going to take our first equation and write it in slope-intercept form. So we have y equals -2x plus 5 because we subtracted 2x from both sides. And then over here, we add 4x to both sides and then divide by 6. So we're left with y equals 2/3 x plus 2. So if you look at this graph here, The blue line is going to be our y equals negative 2x plus 5 because we have an intercept of 5 and we go down to right 1. And then this one here is going to be our y equals 2/3 x plus 2. We have a y-intercept of 2. We go up 2 and right 3. And then this point is 9/8, 11/4. So let's go ahead and take a look at an example where we're actually solving this algebraically. So those were just a couple of examples where we could see what it looked like in terms of a graph. But let's look at something where we're going to solve a system of equations using substitution, and then we're going to do elimination next. So we have this equation 2x plus 3y equals negative 3, and then we have the equation 4x minus y equals positive 3. And what you want to do is you want to pick one of the equations and then solve for one of the variables in terms of the others. Meaning that basically we want to take one of these equations and we want to isolate a variable. So if you look at what's going to be easiest, it's going to be the second equation here. It's going to be getting y by itself because it's not attached to any number. So this is the only one where you have a y that does not have a coefficient. It just makes it easier to solve because then you don't end up with fractions or anything like that if you don't have fractions in the original. So if we're getting y by itself, we would subtract 4x from both sides and multiply or divide everything by a negative sign. So we'd get y equals 4x minus 3. So that's our first step. And then what you do is you take the y equals 4x minus 3 and you substitute that result into the remaining equation for y. So we know that y is equal to 4x minus 3, so we're going to look at our first equation, and then in place of y, I'm actually going to put 4x minus 3. So I have 2x plus 3 times 4x minus 3, because that's equal to y, equals negative 3. And then you go ahead and distribute and solve. So this shouldn't be too difficult. Hopefully you're familiar with this. We're going to take our 3 and distribute it. So 3 times 4x gives you 12x. 3 times negative 3 gives you negative 9. And then we combine our like terms. So 2x plus 12x is going to give you 4x. And we add 9 to both sides. So we get 14x, not 4x. So we get 14x equals 6, and then we divide both sides by 14. So we get x equals 6 over 14, which is going to simplify to 3 over 7, since these are both divisible by 2. So I know that x is 3 over 7, and then all you need to do is you need to do back substitution to get the remaining value. So what I would recommend doing is using your original equation from step 1, the y equals 4x minus 3 that you created, and substituting your value that you just found back in for x. So we know that y equals 4 times 3/7, since that is your x value, minus 3. And if you actually do this and you simplify, you get y equals negative 9/7. So if we want to check the solution, what we should do is we should take our 3/7 for x and our negative 9/7 for y, and we should plug it into both of our original equations. So we'd have 2 times 3/7 plus 3 times negative 9/7. That's 2x plus 3y. And if you actually do that, you will get negative 3. And you could do this in your calculator to verify. It shouldn't take too long. And then you would do the same thing with the second equation. So you take 4 times x, which is 4 times 3/7, minus negative 9/7. So this is going to become plus 9/7. And if you do this, you will get 3 as well for this one. So this one works, and this one over here works as well. So our solutions are good. And this just verifies that you did all of the math correctly. Okay, now we can also solve systems of equations by elimination, which is the method that we're going to use when we have 3 equations and 3 variables. So there are a couple of rules that we have to kind of stick with. One thing you can do is you can interchange any 2 equations in the system. You can also multiply or divide each side of an equation by the same non-zero constant, and then you can replace any equation in the system by the sum or difference of that equation and a non-zero multiple of any other equation in the system. So let's take a look at how some of this stuff works. So let's say we want to solve the equations 2x plus 3y equals negative 1 and 2x minus y equals 3. So if we want to solve this using elimination, what we're trying to do is we're trying to get rid of either x or y when we add these two together. So if you take a look, there are multiple different ways to do this, but step one is going to be to multiply both sides of one or both of the equations by some constant so that the coefficients of the variables are additive inverses, meaning that they're going to cancel when we add them together. So for example, if we were to multiply this first equation by a -1, we'd end up with a -2x and a positive 2x down here, which would cancel. So that would do the job. Or we could multiply this equation down here by -1, because if we multiply this by -1, then the 2x and the -2x are going to cancel. Or we could multiply this bottom equation by 3, because I would have a positive 3y up here, and then I'd end up with a -3y down here, and those would cancel. So if you look at what is actually done, we did the last thing, which was to multiply by 3. It absolutely doesn't matter what you do. Any of the three options that I walked through would work. You could also multiply this equation by 1/3, which is probably the not so nice solution because you're dealing with fractions. But if we take this second equation and we multiply everything by 3, what we're going to get is 6x minus 3y equals 9. So we have to multiply both sides of the equation by 3, so that's this right here. And then we just keep this first equation as is. And then what we're doing is step 2, which is just adding the two equations together. So we have 2x plus 3y equals -1 and 6x minus 3y equals 9. And then we just add them together. So the x terms, 2x plus 6x, become 8x. The -3y and the positive 3y are going to cancel, become 0. And then we just get equals 8. So we have 8x equals 8. And then we divide both sides by 8. And so we get x equals 1. And then you use a little bit about what we learned about substitution to find the original value. So, or the other value, the missing value. So if you know that x is equal to 1, what you're going to do is you're going to use one of your original equations to find the value of the remaining variable. So it looks like we've chosen the second equation here. It doesn't really matter which one you choose. But I know that 2x minus y should equal 3. So all I'm doing is I'm plugging x equals 1. So I'm plugging 1 in for x into my equation. So I have 2 times 1 minus y equals 3. And if I go ahead and subtract 2 from both sides and multiply or divide by a negative sign, I get y equals -1. And then we want to check the solution. So we know that we have x equals 1, y equals -1. So we plug them again into both of the originals to make sure that it works. So I have 2 times 1 plus 3 times -1. If you simplify this, you're going to get -1. And then the second equation, I have 2 times 1 minus -1, which gives you a positive 3. So both of those work. So we write our solution as a coordinate 1, -1. It's always x and then y. Okay, let's look at an example where we have kind of an applied situation. So let's look at something where we have movie theater ticket sales. So a movie theater sells tickets for $8 each, with seniors receiving a discount of $2. One evening, the theater took in $3,580 in revenue. X is going to represent the number of tickets sold at $8, and Y is going to represent the number of tickets sold at our discounted senior price of $6. So we want to write equations that relates these variables, and then we're going to solve them. So if you take $8 and multiply it by the number of tickets that you sold at that price, and then you take $6 and multiply that by the number of tickets that you sold at that price, and you add the two together, that's going to give you your total revenue of $3,580. So that's one of the things we're going to do. And let's say that we also know that 525 total tickets were sold. So we want to write another equation. So this allowed us to write an equation related to revenue. And now we're going to write an equation related to the number of tickets that were actually sold. So if we know that the total number of tickets was 525, that means if we add x and y together, we should get 525 tickets. So we have our two equations here, which have just been rewritten here. 8x plus 6y equals 3580, and x plus y equals 525, and then we want to go ahead and solve them. So we're going to use elimination, and it looks like we could have done any number of things, but probably the easiest is to multiply this equation either by -8 or -6, so that either x or y cancels. So it looks like what was done is we took this second equation and we multiplied everything by a -6. So when you do that, you get a -6x minus 6y equals -3150. And then when you add it to the original first equation, the negative 6y and the positive 6y are going to go away. Those just become 0. 8x minus 6x is going to give you a positive 2x, and then 3580 minus 3150 is going to give you 430. So we have 2x equals 430, so x equals 215. So we know that the number of $8 tickets that was sold was 215 tickets, and then we also know that x plus y is 525. So all we have to do in order to get our y value is take our 525 total tickets and subtract the 215 that we already know we sold at a normal price, and we get 310 discounted tickets. So we know that 215 non-discounted tickets were sold and 310 senior discounted tickets were sold. So this is just, with applied problems, make sure you're thinking through it logically. You should end up with two equations, each with an x and a y, and then you're going to use either elimination or substitution, whichever you prefer, in order to solve for one of the variables. And then you use one of your original equations in order to find the value of the other variable. Okay, let's look at something where we have an inconsistent system of equations with two variables. We're also going to look at this at the end of the video where we have three different variables, but let's take a look where we just have two. So if we have x minus 3y equals 2 and negative 2x plus 6y equals 1, if we want to solve this, we can do it any number of ways. I think probably the easiest way, they've used substitution. Probably I would have used elimination and multiplied this top equation by 2, but it doesn't really matter too much. So they're taking this first equation and they've solved for x. So we have x equals 3y plus 2. And then what we do is we take this 3y plus 2, this is just substitution, and we substitute this in for x here. So I have negative 2 times 3y plus 2 plus 6y equals 1. And if we go ahead and distribute this, we have negative 6y minus 4 plus 6y equals 1. Negative 6y and plus 6y, those are just going to go away. And we're just left with negative 4 equals 1, which we know that this is not a true statement. We know that negative 4 is not equal to 1. So since the statement is false, we conclude that there is no solution. So another thing that we could say is that the system is inconsistent. And if you think back about when we talked about inconsistent lines, these are actually two parallel lines here. So there is no solution because they never intersect. Okay, now let's look at expressing the solution of a system of dependent equations containing two variables. Again, we're going to look at this with three variables in just a little bit. But let's say we have x minus 3y equals 2, and we have negative 2x plus 6y equals negative 4. So you can either use substitution or elimination to solve this. So it looks like they've taken the first equation, solved for x, so we get x equals 3y plus 2. And then we go ahead and we plug 3y plus 2 in wherever we see an x in the second equation. So we have negative 2 times 3y plus 2 plus 6y equals negative 4. So what I want you to do is I want you to take 10 or 15 seconds, go ahead and distribute and combine like terms and see what you get for a solution for this one. Okay, so hopefully when you distributed, you got a negative 6y minus 4 plus 6y equals negative 4. And then the negative 6y and the positive 6y, those just become 0. So you get negative 4 equals negative 4. Now we know that this statement, unlike the last one that we had found, is actually true, but we don't have any variables. So what we say is that the two equations are equivalent, so the equations are dependent. So in order to write our solution, what we would actually do is we'd say that it's all x's and y's such that x is equal to 3y plus 2. Because what we've done is we've taken this first equation and we've solved for x. So we have x equals 3y plus 2. We had gotten that right down here, and that's what we used to actually solve it. So we've written our solution set as x comma y such that x is equal to 3y plus 2. Okay, now let's take a look at solving systems of three equations with three variables. So there are There's a little bit of methodology involved, but really, if you do several examples, I think the idea will kind of stick with you and it won't be so difficult. It just takes a little bit of time to grasp, so don't get too frustrated if it doesn't make sense right away. But there are many different ways to solve these types of problems, and typically you're not going to solve them the same way as the next person. So elimination method is typically the easiest, where you're getting rid of some kind of variable. So what you're going to do is you're going to have three equations. So you're going to take them in pairs. So you're going to have two pairs of two. And the goal is to eliminate the same variable each time in those pairs. So you have to use each of the equations at least once. Okay, so you have three equations, you have to use all of them. And then what you're going to be left with after you've eliminated the same variable two different times is you're going to be left with two equations with two variables. And then at this point, you can solve it using any approach that you would like. Either elimination or substitution is going to be your best bet. I think elimination is normally easiest, but that's kind of up to you. So let's take a look at what our solutions can look like, and then let's do some examples. So if we have three planes here, you can notice that they're all intersecting at one point. So this is a consistent consistent system where we have one solution. We can also have something like this where we have three planes that are intersecting at a line. So this is a consistent system with an infinite number of solutions. And then we could also have something like this where we have an inconsistent system with no solutions at all. So we can have all of the same kinds of solution sets that we had just with two equations and two variables, except now we're talking about planes instead of just lines. So let's take a look at this right here. So we have 2x plus y plus z equals 4, negative 3x plus 2y minus 2z equals negative 10, and x minus 2y plus 3z equals 7. So what we want to do is we want to use elimination, and what we're attempting to do is we're attempting to use two different pairs of equations to get rid of the same variable each time. So if you take a look at this, I want you to go ahead and take a look and see if you can come up with what would be the easiest way of doing this. I'll give you a few seconds to take a look at that. Okay, so there are a lot of different things that you could have decided to do. For example, we could take the first and the second equation, and we could multiply the first equation by 2 to get rid of the z, okay, with this one. And then we could take the first and the third equation and multiply the first equation by negative 3 to get rid of z again. I think the easiest way, and I'm not sure what's done, so we'll see in a second, but I think the easiest way is if we take the second and third equation, and if you look, the y's are already going to be eliminated, so that's pretty easy. And then if we take the first and the third equation, and we multiply this first equation by 2, you're going to have a 2y and a negative 2y, so those are going to cancel as well. But let's see what we actually did. Let's see, so it looks like we took... Okay, it looks like we're eliminating x's in this case, which is fine. So we have our first equation, 2x plus y plus z equals 4, and then we've taken our third equation and we've multiplied everything by a negative 2, because we're going to have a positive 2x and a negative 2x, and then those are going to cancel. So when we multiply our third equation by negative 2, we're left with negative 2x plus 4y minus 6z equals negative 14. And then we add the two together, and we have 2x minus 2x, that's going to cancel. Y plus 4y is going to be 5y. Z minus 6z is going to be negative 5z. And 4 minus 14 is going to be negative 10. So what I would do at this point is put a little star by your equation so that you don't lose it on your paper. Because what you'll find when you're doing these is that it's very easy to actually lose your solutions, and then it takes a little while to kind of figure out where you were. So this is going to be one of your starred equations, so I'd stick a star next to this one. And so we've eliminated x, and we use the first and third equations. So now it means that we either have to use first and second, or second and third equations in order to eliminate x again. And if you take a look, I think it's going to be a little easier to use the second and third because they already have opposite signs. So this one is a -3, this one is a +1. So if we take our third equation and we multiply everything by +3, we're going to have a -3x and a +3x, and those are going to cancel. So we have our second equation, which is -3x plus 2y minus 2z equals -10. And then we take our third equation and we multiply everything by 3. So we have 3x minus 6y plus 9z equals 21. And then we add that together and we get -4y plus 7z equals 11. And this is the other equation that I would stick a star next to. And then at this point, you should have two starred equations, and then you're going to figure out how to put those together to go ahead and solve. So we're going to move the two equations so that they're next to one another and figure out how exactly to solve them. So this can be done any number of ways. You could solve for one variable and substitute it in. It doesn't really matter, but I want to give you maybe a minute to see if you can solve for y and z. All right, so let me give you a minute to go ahead and try that on your own. Make sure you're able to get those values. If you're looking for a hint, probably what I would do is eliminate either z or y using elimination. So probably what I would do is I'd multiply this equation by 4 and this equation by 5 so that you're going to have a 20y and a -20y. But there are many different ways that you could do this. Okay, so hopefully you were able to solve this. Like I said, we can take this first equation and multiply everything by 4. Take the second equation, multiply everything by 5. For the first equation, we'll get 20y minus 20z equals -40. And for the second equation, you'll get -20y plus 35z equals 55. You'll add the two equations together, and you get 15z equals 15. So we get z equals 1. And then what you're going to do is you're going to take one of your starred equations, and you're just going to substitute z equals 1 into that equation. So we had an equation that was 5y minus 5z equals -10. We're just taking that and we're just going to plug z equals 1 in. So we know that 5y minus 5 times 1 equals -10. So we get y equals -1. I would make sure that as you get these solutions, you actually circle them on your paper, so again, you don't lose them. So we know that z is 1, y is -1, and then what you do is you just use one of your original equations in order to find x. So let's see. The third equation is easiest because x is already it has no coefficient, it's just a coefficient of 1. So we have x minus 2 times -1 plus 3 times 1 equals 7. And if you solve this, you just get x equals 2. So our solution set is written as 2, which is our x value, comma, -1, which is our y value, and then comma, and then 1, which is our z value. Okay, now let's take a look at something where we have an inconsistent system. Whoops, sorry about that. So we have 2x minus 3y minus z equals 0, negative x plus 2y plus z equals 5, 3x minus 4y minus z equals 1. Now if you take a look at this, the z's should appear as pretty easy to eliminate because we have a negative z and a positive z, and then we have the same thing here, negative z and positive z. So if we put oh, it looks like that's not actually what's done here. That would be the easiest thing to do, but that's okay. What's actually done here is we're taking the second equation and multiplying everything by 2 so that it's going to cancel with our x. So what we end up with is negative 2x plus 4y plus 2z equals 10. So all we've done, again, is just taking the second equation and multiply everything by 2. And if we add these together, we get y plus z equals 10. And then it looks like what we're going to do next, this would be one of our start equations, is we're going to take the second equation and multiply everything by 3 because then it will cancel with this third equation. So we have 3 times negative x plus 2y plus z equals 3 times 5. And then we have our third equation of 3x minus 4y minus z equals 1. We go ahead and just distribute the 3 through. And we add them together. So we should get 2y plus 2z equals 16. So then we take our two start equations and we're going to stick those together. And we can multiply the first equation by negative 2. That's probably the easiest thing to do. So we get negative 2y minus 2z equals negative 20. And then what you should notice is negative 2y and 2y are going to cancel. Negative 2z and 2z are going to cancel. And we're just left with 0 equals negative 4. Now, we know that this is not a true statement. So since the statement is false, we're going to conclude that there is not any solution. So we would say the system is inconsistent. And we looked at a couple of examples of what that might actually look like. Okay, now the last thing in this section is expressing the solution of a system of dependent equations containing 3 variables, which is probably the most difficult thing to do. So if you take a look here, we just have 3 equations, and you can again solve these any way that you'd like. It looks like what they've done is they're just eliminating the x's. Okay, so we're taking this first equation and multiplying everything by negative 2. So I want you to go ahead and take this first equation, multiply everything by 2, eliminate the x's. You're going to end up with an equation with 2 variables. All right, so you're going to go ahead and distribute and combine. And then once you're done with that, I want you to take the first and the third equation and multiply the first equation by negative 4 in order to get rid of the x's again. So I'm going to give you about a whole minute to work on that, see if you're able to get your 2 start equations. So hopefully for this first equation, you were able to get negative 3y minus 3z equals 0. So we just took the first equation, multiplied everything by negative 2, and then added the 2 equations together. And then hopefully you took the first equation and multiplied by negative 4, and then let me give you another minute to go ahead and finish up this step. You're going to put these 2 equations together. So hopefully as your simplified version here, you got negative 4x minus 4y minus 8z equals negative 4 when you went ahead and multiplied everything by negative 4. Then if you add the 2 together, you should get negative 3y minus 3z equals 0, which if you look at these 2 equations, if we put them side by side, hopefully you'll see are exactly the same equation. So if we subtract one from the other, you're just going to get 0 equals 0, okay? So this statement is true, unlike the last one. I think we had -4 equals 0 or something like that. We know that this statement is actually true, but we don't have any variables. So the equations are going to be dependent, all right? So if we take a look at this example right here, if we just look at the -3y minus 3z equals 0, if we solve one in terms of the other, we know that y is going to be equal to -z. So for example, if we go ahead and we add the 3y to both sides and divide by 3, you're just going to get positive y equals -z. So we know that y is equal to -z. And then if we take our original equation, x plus y plus 2z equals 1, and we go ahead and substitute in what we actually know, okay, which is that y is equal to -z. If we plug -z in here, we get x plus -z plus 2z equals 1. And if we go ahead and simplify this and solve for x, we would get x equals -z plus 1. So what we've done is we've taken x and y and we've solved both in terms of z. So we've gotten x and y both by themselves and in terms of z. So this is how you would actually write your solution set. It would be all x, y, z's such that x is equal to -z plus 1, y is equal to -z, and z is equal to any real number. Now, if you had solved for something different, it's possible that your solution looks a little bit different, which is completely fine. So we could have solved z for y and then done the same thing with x, and we could have, it could have resulted in an equivalent but seemingly different looking type of solution that also would have been fine. So that is it in terms of the material for this week. I want to go ahead and ask if there are any questions for anyone who's logged on live for section 12.1 or any of the other sections that we've done recently that you're just stuck on. Okay, so it does not look like there are any questions. Thank you so much for watching. Good luck with the material, and we'll be back next week for an exam review.